Hello, everybody. So today we're going to start going down the path of something that I'm very excited about because I haven't done it before. So this is going to be a learning experience for all of us. And what we're going to do is to think about what you could call one of the secrets of life, which is defiance, which is how you defy equilibrium for fun and profit, how you burn energy for fun and profit. And as I said, this is completely new for me, so you'll have to bear with me sometimes, and hopefully we'll come up with interesting things as we develop these lectures. All right. So in the previous few lectures, we talked about statistical mechanical models, and in particular, I showed you how these StatMech models could be unreasonably effective. Like they worked really well. So just as a reminder, what I'm showing you here is a set of predictions for the level of gene expression. Switch to the pointer. For the level of gene expression as a function of the number of repressors for an architecture where you have a repressor that doesn't let the RNA polymerase bind to the DNA. Each one of these curves corresponds to different settings of these regulatory parameters are the binding energy of the repressor to the DNA and also the number of promoters. So how many copies of your gene do you have? How does that compare to the number of repressors that you have? The point was that using StatMech, we could come up with all these theoretical predictions before we took any data. This is a zero parameter fit. Then we went and took the data, and what we showed is that to a large extent, we could predict the input-output functions for just knowledge of the DNA sequence. Not only that, these curves look very different, but what you can show is that the reason they look different is because we're not plotting the right x-axis. If you plot instead an effective repressor number, what you show is that the fault change, all the data for the fault change in gene expression collapses onto the same master curve, which tells you that we have identified the natural variable of the system. In some sense, if we are anthropomorphizing, that we have identified the variable that the cell cares about. Okay, so it's crazy that this works so well, and it's not just crazy because like we see how well it works, but also because of the assumptions that underlie these statistical thermodynamic models. Like remember that we went through a whole protocol, right? That consisted in coming with the states that your system can be found in. This is for here. I'm showing you some states for a system that can be brought around the nucleosome, and the details don't matter. But then for each state, you come up with a statistical weight, right? Using Boltzmann recipe. And one of the main assumptions of this whole set of statistical mechanical models is that in none of these processes, you're spending energy. Let me make myself a little bit smaller so you guys can see this. 1 second. There. That works better. Okay, great. So I'm just curious, like clearly you can do a lot of things in this context, but it's also true that, biology can be, like living matter cannot be in equilibrium, otherwise it would be dead. So, what happens when you relax this assumption of no energy consumption? What are the sorts of things that you can do when you spend energy that you cannot do when you don't spend energy? Okay, and what we're going to do throughout the next 2 weeks, probably maybe 2.5 weeks, is think of the different ways that you can spend energy in order to defy the forces of equilibrium. Okay, so some of the examples that we're going to focus on are, you can spend energy to create a gradient, right? So, to have more, for example, ions inside the cell than outside the cell. You can spend energy to increase the fidelity of molecular processes. For example, think of the process of translation. How often do you incorporate the right amino acid versus the wrong amino acid? You can use energy to adapt to environmental changes, and so here what I'm showing you is the response of the eye in response to the intensity of light. And basically, as our eyes can adapt. Like if you're in a situation that is very bright, the eyes adapt so that they can see small changes from that baseline that is very bright. And if you're in a very dim environment, that after a while your eyes adapt such that now you can see small changes within that baseline of a dark environment. And in order to do this sort of adaptation, you need to spend energy. Socks before shoes. What do I mean by this? Like in biology, we love drawing diagrams where there's only one arrow. Okay, and to have one arrow to encode for temporal ordering, you need to spend energy. To make sure that you put your socks on before you put your shoes on, you need to spend energy. Otherwise, you're going to have all sorts of weird complexes, such as a foot shoe complex that doesn't include the sock. You can also build energy to create these self-organized dissipative structures. Like think of the mitotic spindle, for example, where you got all these microtubules that are constantly being assembled and disassembled in order to create this seemingly stable structure that then can slowly separate the chromosomes inside a cell. You can use energy also to encode for molecular states dynamically. So here are the types of things I'm thinking about is signaling, how you can add and remove phosphate groups, ubiquitin groups, acetylation and such. And also obviously you can use energy to do transport, to do work, to move things around. Okay? And once again, the idea is to grab a few of these case studies in order to get a sense of the power that you get when you go beyond equilibrium thinking and when you start thinking of what you can do when you spend energy. Let me just remind you that this is by far not a done topic. Like this is really something at the boundary of our understanding right now of living matter, I would say. And I wanted to show here is that our confusion about the nature of living matter dates way back. Okay, so here on the left, I'm showing you the original paper from Robert Brown that described so-called Brownian motion. And all I want you to notice is that he talks in the title about the existence of active molecules in organic and inorganic bodies. Like he thought these molecules were active, were burning energy, were somehow using energy to move around. Okay, and it wasn't until the 1900s with Jean-Baptiste Perrin and Albert Einstein that we started figuring out that diffusion wasn't the result of like an energy consuming process, but just the result of collisions between different molecules in a solution that otherwise is in equilibrium. Okay, so again, all I'm saying is that just like before, we're still a little bit in the shadow in terms of our understanding of what it means to be active and what are the consequences of being active. Okay. All right. So let's start thinking a little more deeper about what it means to be active, and let's use a little example of a so-called anthropomorphic egg that my 4-year-old is super excited about, and his life can be summarized in just a few short lines, because Humpty Dumpty sat on a wall, and Humpty Dumpty had a great fall, and all the king's horses and all the king's men couldn't put Humpty together again. And the point of this is that it's very clear to you, it's very clear to my kid, that once you fall, it's hard to put you together again. It's hard to go back in time. Incidentally, if you have kids, you might enjoy also reading them this book, which is After the Fall, which is how Humpty Dumpty actually got back up together. It doesn't have to do with anything with our course today, but it has really nice drawings, and it's actually a really cute book, so I highly recommend it. But let's go back to this idea of irreversibility. What do I mean by that? Let me show you two scenarios. Okay, let's focus on the scenario on the left, where I have two little domains, two little boxes. Okay, one with a lot of molecules, one with fewer molecules. There's a partition between them, and I open that partition, and now molecules start flowing from the box that has higher concentration towards the box that has lower concentration. And our intuition tells us that the system will reach equilibrium after some time once the concentration of the left is equal to the concentration of the box on the right. Okay? And this looks completely natural to you. Now let's imagine this other idea. I start with a situation where the two boxes have the same number of molecules. I open the door, and now molecules start flowing from one box to the other, such that at the end of the experiment I have a concentration gradient. Like clearly this goes beyond this goes beyond our intuition, right? This doesn't happen. This is running time in the backwards direction. Okay? And this is the type of thing that Maxwell, when he was starting to think about statistical mechanics, wondered about. Okay, and in a letter to Tide, who was one of his contemporaries in thinking about StatMech, what he wrote is, but if we conceive of a being whose faculties are so sharpened that he can follow every molecule in its course, such a being, whose attributes are still as essential finite as our own, would be able to do what it is at present impossible to us. For we have seen that the molecules in a vessel full of air at uniform temperature are moving with velocities by no means uniform, though the mean velocity of any great number of the arbitrary selector is almost exactly uniform. So Maxwell here was starting already to figure out that there's a distribution of velocities inside a gas. Okay, and this has very much to do with the Boltzmann distribution that we were playing with. Now, let us suppose that such a vessel is divided into two portions, A and B, by a division in which there is a small hole, and that a being who can see the individual molecules opens and closes this hole so as to allow only the swifter molecules to pass from A to B, and only the swifter molecules to pass from A to B, and only the slower ones to pass from B to A. I think the text is repeated, sorry. He will thus, without expenditure of work, raise the temperature of B and lower that of A, in contradiction to the second law of thermodynamics. Okay, so what is Maxwell thinking? He didn't quite think of a demon, but then the people started talking about this being as a Maxwell demon, and the idea is that the demon allows you to run the movie backwards if you're willing to pay. Okay, what does this mean? That the demon is going to open the door and only leave it open, only let fast particles move to the left, for example, such that at the end of the day you have a concentration gradient, or in the case of Maxwell's example, you have a gradient of temperature. Okay, and people have been thinking about this concept of the Maxwell demon for a long time. There's a great article by Chris Jarzinski that is on the website, where he reminds us of the huge amount of energy that is stored around us. He tells us that a liter of air, even though it weighs less than half of the weight of a penny, it contains enough thermal energy to lift a 7 kilogram bowling ball more than 3 meters off the ground. Okay, so this is a super cool estimate, and you will do it as one of the homework problems this week. But he talks about a gadget able to harvest that amount of energy by converting the erratic movement of colliding molecules into directed motion could be very useful indeed. And once again, of course, the second law of thermodynamics forbids it. Any device whose sole effect is the extraction of energy from a single thermal reservoir and its conversion into work. But that prohibition has not prevented nearly 150 years of imaginative thinking about the possibilities and impossibilities of rectifying thermal noise, changing it from random to directional. Right, so basically the Maxwell demon is harvesting this thermal noise and turning it into useful work. And that goes completely against the second law of thermodynamics, which will be the topic of the rest of the lecture today. So what can this demon do? Well, this is a little bit repetitive now, given the one of the slides I showed you a little bit ago. But basically, it can act on the processes of the central dogma. And once again, we're going to think of translation fidelity, and if we have some time, and if I figure this out, actually this is stuff that I'm actively trying to figure out, we'll also think of how energy expenditure, how the demon can help us in the process of transcription. It can help you creating concentration gradients. Again, the demon can open and close the entrance to the cell, such that you get more ions inside the cell than outside the cell, for example. It can help you with directional transport. How do you pack DNA into a bacteriophage, for example? And there's also examples having to do with chromosome segregation. You got these paired chromosomes by by cohesins and such, and somebody has to cleave them in. So they're aligned in metaphase, and somebody has to cleave them so that in anaphase they can separate from each other. Okay, so these are all examples of what we call demonic biology. And what I want to start doing today and then over the next few weeks is to start thinking hard about what is the price that this demon has to pay in order to set up these situations that go seemingly against our equilibrium thinking. Okay, and in order to do that, the first thing is that we need to establish the baseline. I talked a bunch of times about the second law of thermodynamics, and I hinted at that during our discussions on gene expression. But what I want to do is spend some time now thinking explicitly about the second law of thermodynamics and what it means and what it implies. Okay, so that's what we'll do in the next little vignette.